We are Team 2. My name is Kevin Alvarez.
And my name is Jose Gomez. And we'll be talking about wind energy today. First, we're going to start talking about the history of wind energy. Wind energy has been used for thousands of years. The first ever actual windmill used was in Persia in 500 BC. It wasn't until the late 1800s that steel blades were being used for wind turbines. This made the wind turbines a lot more efficient. In 1981, the Viterna method developed was a calculation for wind turbine performance that is still used to this day. The modern use, in 1992, Energy Policy Act authorized a production tax credit of 1.5 cents per kilowatt hour of wind power generated electricity. In 2008, the U.S. Department of Energy pushed for a 20% by 2030 initiative. This graph here is a global annual installed wind capacity from 1997 to 2014. In 2014, the global annual installed wind capacity was 51,477 megawatts. This here is a graph of the cumulative installed wind capacity, which now by 2014 is at 370,000 megawatts. These graphs here show the countries with the most capacity installed in 2014. As you can see, China has the most, which is the red, and the same for the cumulative capacity in 2014. These cool looking airplanes here, the Makani Airborne Wind Turbine, or AWT, they have the ability to rise to high altitude and generate consistent energy at higher speeds than ever before.
So how do these things work? How does a generator work? How do we produce wind power into electricity? So a generator is basically something like this. It works on the principle of electromagnetic induction. We have a spinning rotor that's excited by a battery source or a permanent magnet, and it spins around inside a stator. The stator is induced voltage that is the power that comes out of the generator. In a wind turbine, this is how it looks. The generator will be right here in the back. So the generator, in order to produce the correct frequency to connect to the grid, needs to spin at a certain speed. How is that achieved? We have a gearbox. The gearbox spins the shaft from the input to the output at the right RPM, or revolutions per minute. So for a 4-pole rotor, spinning at 1800 RPM will produce 60 hertz. 60 hertz is the standard for the US. For European nations, it's 50 hertz. So how do we achieve the initial rotation of the windmill? We have these blades that act as airfoils. When the wind blows past them, there's a pressure difference, and it allows them to start moving. It's all dependent on how they're pointed into the wind. How they're pointed into the wind is controlled by the pitch mechanism that can actually rotate these blades so they have the best angle of attack towards the wind coming in. Now, if they're pointed in the wrong direction, they're not going to create any power, right? So in order to point them in the right direction, we have an anemometer with a wind vane, and that can detect which way the wind is coming, and that sends a signal to the controller. The controller then sends power to the yaw drive and the yaw motor, and it will actually turn the entire assembly. All of these things are housed in a nacelle. The nacelle, as it's stated here, is just like one big aerodynamic duct that covers, like your hood or an engine nacelle in an airplane. We also have a brake. When you're performing maintenance, you want this thing to be stopped. So we have a brake. It can be a mechanical brake, it can be an electrical brake, it can have many different types. So there are two major types of wind turbines. The vertical axis wind turbine and the horizontal axis wind turbine, like I showed before. The horizontal axis wind turbine contains a pitch system, like I stated, in order to maximize efficiency. The vertical, on the other hand, doesn't need a pitch system because it's omnidirectional. Omnidirectional means that wind coming from any direction will spin the blades or the rotors. There are other smaller types of wind turbines, but we won't get into that. So these are the two major ones. Now, when you're saying, hey, which one's better than the other? Well, the vertical axis turbine is better than the other one. Now, the only problem with that is that we haven't developed one that can create as much power as a horizontal axis wind turbine. So the horizontal axis wind turbines are the ones that you see in really big wind farms, like the ones in Denmark, or the ones in the US, or the ones in Europe. So we say, okay, it's better all around. It has better efficiency, it doesn't need a mechanism to steer it, it doesn't have that. So we say, okay, well, it has its pros and cons. And these are the major parts. As we see here, when you're doing maintenance, especially for a vertical axis, the generator, gearbox, and all that assembly is here. And it's easier to get to. In a horizontal axis one, it's all the way up here on the tower. So you would have to either get a crane or all these other stuff that, in hundreds of meters in some cases. So.
Hello, my name is James Taylor, part of Team 2, and now we are going to talk about the economics of wind energy. So, wind energy is essentially free due to the fact that it is such an abundant natural resource. Wind energy, wind actually comes from solar energy, and so long as the earth is spinning, then we will have wind, always. So, manufacturing wind turbines has a significantly high startup costs. So there's factors that go into, that must be thought about before investing into wind turbines or wind farms, and those are the following. You have to think about the cost of the turbine, cost of the installation of the turbines, the lifetime of the turbines, basically how much longevity are you going to have for each turbines, because you're investing in each one. So that's about 20 years. Then you have to worry about the annual maintenance costs. The annual maintenance costs are actually pretty low costs. They're not anything where you're going to have to keep funneling in money to maintain them over that 20-year span. So that is where you stretch out your dollar. Now, then continuing on, there is the reference price received and or for the electricity produced, and then you have your incentives from the government. Okay, so when going in and investing into something like a wind turbine or a wind farm, suppliers can help you decide what you need, because due to the fact that wind varies so often and it depends on where your location is, like in Minnesota, for example, it's much colder, so the wind might be much more dense than it is in, say, Florida. So you might actually produce more wind power in Minnesota than you would in somewhere like Florida. So you need to go to a supplier that will help you get an idea of what your initial costs are going to be and what's going to cost overall for your entire project. Now, for small turbines, it can cost as low as about approximately $5,000 to $7,000 in initial cost, which is not very expensive. Now, maintenance costs can be only about 10 to 20% of that initial cost. And then for large wind farms, those can cost millions of dollars, because you have a big group of wind turbines. And that installation and maintenance of a large wind farm can account for up to 35 to 55% of your investment. Now, there is two different types of installations for wind farms. You have your onshore and your offshore. So your offshore could actually cost 20% more than your onshore, due to the fact that you're going to have to workers are going to have to create a foundation further and further out into the ocean. And the further out they go, the less realistic or the more work it costs to make a foundation. And also you're going to have manufactured bigger, taller wind turbines, because a lot of it's going to be submerged underneath the ocean. The price per kilowatt hour, they convert 20 to 40% of the energy in the wind. So 20 to 40% of that wind, it can be converted into energy that is useful. The power output of a wind turbine is a function of the cube of the average wind speed. So if your wind speed doubles, then your power output will increase 8 times. Also, given the height of your wind turbine, the higher it is, the more potential power output you will have. And in 2011 and 12, the price under long-term power purchase contracts in the US averaged 4 cents per kilowatt hour. So the operation costs have decreased significantly. They've actually halved. That concludes the economics of wind power and wind turbines.
All right, now we're going to talk about the pros and cons of using wind turbines. Weighing out the pros and cons is always really important. You want to know if your investment is going to give a good return or not, or anything like that. All right, the pros of a wind turbine are clean, renewable energy, which is very important. The wind, very easily accessible. Government incentives, always a good thing. And promise of a cleaner tomorrow. The cons are expensive startup costs, as we have talked about. A lot of distance needed between them lead to also high real estate costs. Things like that aren't always taken into account, and they need to be. They also, believe it or not, pose dangers to animals and humans. Ethics and safety. This first picture here is a picture of a generator fire. Then these are wind turbines getting struck by lightning, also can cause a fire in some cases. And this picture here is the breakage of a tip of a rotor blade. That's real dangerous because the blade can break off and fly out and hurt somebody. Ethics and safety continued. Safety is every engineer's #1 concern. Failures must be prevented. All things need to be taken into account to prevent those failures. Regular scheduled maintenance is a real good prevention strategy, and safety precautions must be strictly reviewed and enforced. This here is a table of the different kinds of failure distributions in a 250 wind generators for a 10-minute exposure to 35 meter per second gale winds. As you can see, the highest percentage are in the total tower and the cell collapse, yaw control failure, and blade tip failure. This here is our conceptual design. As you can see, we chose a vertical axis turbine with carbon nanofiber blades and aluminum hub. The simple circular shape and thickness of the blade lead to lower manufacturing costs. Given the omnidirectional state of these vertical axis turbines, just like talked about before, it's easier to maintain and to fix. It decreases risk of injury from broken blade tips. The carbon fiber blades are light, strong, and more cost-effective than current materials that are being used to make these vertical axis wind turbines. The material and color, I think, makes it look a little nicer also, which is another issue that people talk about. They don't like the way these wind turbines look. Here's a video of our wind turbine turning. And that's it. That's the end of our presentation. Thank you.